All right, well, seeing you. All right, let's talk some more about friction here. And interestingly enough, talking about guardrails on cars. So, even with a single force applied to an object, it is usually not the only force affecting the motion because of friction. Friction is a force that always acts in a direction opposite to motion. Here you go, Will. Don't disturb, we're just getting started here. Okay, you guys know this already. Cool, don't get distracted. You guys know this already, that friction always acts opposite to motion. Due in large part to irregularities, we talked about this before, the two surfaces that are in contact. Even very smooth surfaces are bumpy when viewed with a microscope. We've talked about this. The force of friction between two surfaces depends on the kinds of materials and how much they are pressed together. Rubber, concrete, for example, produces more friction than steel against steel. That's why concrete road dividers are replacing steel rails. Now, you probably don't see these very much anymore. Can anyone tell me where one of those kind of things exists?
Bridge.
Usually on older bridges on like secondary roads or even gravel roads, right?
Yeah.
They will have those kind of, that was common in the 1970s. This is much more common now, especially on larger bridges, main highways. Why is this more effective than this?
That's stronger.
Yeah, it's flared out at the bottom like this, and so the concrete touches the rubber, way more friction than the body of the car rubbing up against the steel sideways there. So how come they haven't replaced all the gravel road bridges with these? Just mainly because of cost, exactly. Not cost.
The one you circled is better?
No, this one's better because it's rubber on concrete instead of steel on steel. That's what they're going towards, yeah. And you see them more and more. When if they replace a bridge, they'll put that in. But
More expensive than the steel.
well, it's probably more expensive to produce. Yeah, I don't know. I'm sure that's the reason. When there is friction, an object may move at constant velocity while a force is applied to it. In this case, the friction force just balances the applied force. That's the key idea that you should already know. Net force is zero, so there's no acceleration. For example, in figure 4.9, train will move at constant velocity when it's pushed just hard enough to almanac friction. Wonder what that word's supposed to be. What do you guys have? It's not almanac. Right here. Did you find it in your sheet?
No.
I'm thinking balance or counteract.
Hard enough to balance the friction as it
Just balances, just hard enough to balance the friction. Right here, this should be balance. Here we have a sack of toys. Santa has dropped his toys out of his sleigh. The sack will fall at a constant velocity when the air resistance balances its weight. This is all review stuff about friction, right? You should know all this. If there's anything in here you don't know, you need to learn it real quick. What's this called? What speed is this when it's like this? Here we have the net forces, 0. What's that speed called, Graham? Graham, enough with the Snapchats. Whatever it is that you're doing, put it away, please. What speed is this, Graham? I'm not asking for a number. What's it called? I'll give you a hint. Terminal velocity. All right, it's how fast it can fall. Okay, does this have anything to... Oh, got a clicker question here. Help us up. Figure 4.6 there, you've got it, I think, as well. Kind of sideways, shows only two forces acting on the book. It's weight and the support force. Does the force of friction act as well? Is friction acting right now? Yes or no? Amanda, we're waiting for you. What? Oh. I did. You get your sticker. You know, for all that I put up with you, free coffee would be. Okay. I have it easy. Okay, what's the correct answer? Oh, the correct answer is no. Who put no? Good for you. Who wants to try to explain? Willie? How come no? You got it right. Does it have to be moving for there to be friction? You're on the right track.
Oh,
You're right. This is not moving.
Stop going to
Not unless the book tends to slide or does slide, right? It's either has to be moving or someone has to be applying a force trying to move it. Like if I did this, if I had like a small pulling force here, then there'd have to be friction, right? You're absolutely right. Early morning? There's probably another one here to make up for it. Okay. Suppose a high-flying jumbo jet cruises at a constant velocity when the thrust of its engine is a constant 80,000 mn. What the heck is an mn?
miles per minute.
No. You're on the right track, just the opposite way. Come on, what's not kilonewtons, but meganewtons. Really big cookies. 80,000 meganewtons. What is the acceleration of the jet? Do I need to turn it on? Oh, I do. Okay, sorry. You tell me. Jumbo jet's flying at constant velocity. Thrust of the engines is a constant 80,000 meganewtons. What is the acceleration?
Oh my god.
V?
I said V, but
One of us go with some
Single cream, half a sugar.
single cream. Oh, what do you have?
You say I'd like a half a sugar and they put half it. What?
Oh, no.
Because I don't.
it's way different.
I don't want that much sugar. I'm trying to lead a healthier lifestyle, Graham. I don't run around eating sugar and muffins every morning. Triple.
No.
You give me a heart attack, man.
Diabetes. Diabetes type 4 right there.
What's the acceleration?
0.
You better have all got this right.
I did not get this right.
Is it 0?
Yes, it's 0.
Oh, my friends. What does constant velocity mean? Not accelerating. I even said it again and I stumbled over it thinking, oh, should I say it again? Well, okay, I'll give it to him. Okay, well,
It's okay, Mr. Brandon. Next one.
make up for it in the next one, Cole, okay?
Reset right now.
Do I have to hit reset?
Yeah.
Okay. What is the force of air resistance on the jet in the previous question? What is the force of air resistance?
I'm going to listen to Bill on this one because Bill got that. Bill's always doing that. Bill.
He's a budding engineer.
So fast.
2.0, Bill DeVos, the science guy. You and I can go into business. I'll be the producer. You can be the on-air talent.
Does Bill Nye still make science?
I don't know.
Oh, he's dead.
No, he's not dead. Come on, you guys!
There's a rumor though.
He does occasionally make appearances.
What is that the thrust of the engines is 80,000 and it's moving at a constant velocity,
It must be.
right? The engines are pushing back with 80,000 newtons. I guess it's going that way. What's the air resistance the other way?
Negative.
I guess maybe you might have been concerned because it didn't say negative. Okay, fair enough. Negative 80,000, right? Acceleration is 0. Ay caramba. Okay, let's talk about pressure. You can put a book on the table, no matter how you place it, back, upright, or even balanced in a single corner. The force of the book on the table is the same. Let me get a book to demonstrate here. Because a lot of people don't understand that.
Doesn't it like Firestone?
Okay. Let's say the book weighs 1 kilogram. 1 kilogram. 1 kilogram.
Okay.
1 kilogram.
We're going to do this thing all thing.
We are?
Yeah.
Okay, now let's say that this is not a 1 kilogram book. Let's say this was a 200 kilogram crate. How would you rather it sit on you? Like this? Like this? Or like that? You'd rather that?
Yeah.
It was more pressure per square inch.
Exactly.
Impulse.
Impulse. Don't confuse them. Can I do something for you, mister? Or you just wanting to learn some physics?
Well, I was wondering if you read this.
Oh, I'll come back later. I gotta finish this.
Where's physics?
Okay, well, don't stand there.
What are you gonna do?
We're talking about pressure and friction. This can be checked by doing this on a bathroom scale where it'll read the same weight in all cases. Balance the book different ways in the palm of your hand. Although the force will be the same, you'll note differences in the way the book presses against your palm. This is because the area of contact is different in each case, and as Graham pointed out, the force, you said force per square inch, right?
Oh my god.
Yeah. Like PSI, what does PSI stand for? Pounds per square inch.
Use that for gas.
Well, it's usually for your tires, right? About 35, 40 PSI in the tire, right? So a pound is actually a unit of force. So in a square inch, there's 30 pounds. That's a fair bit of pressure, isn't it? Yeah. This is because the area of contact is different in each case. The force per unit area is called pressure. More precisely, pressure equals force divided by area of application, or P is equal to F over A.
Would
Go.
that be why like tires are heavier? Like, would it be to deal with that, like with the weight?
What do you mean by tires are heavier?
Because of the air, like the PSI inside the tire.
You mean like they weigh more?
Yeah.
Well, if you weighed, like, are you saying that if you take a tire that's full of air and weigh it compared to the same tire that's uninflated, it would weigh more? That's just because there's more stuff inside. There's more molecules, right?
Yeah.
The air has mass, absolutely. Yeah. P is the pressure, A is the area, force is measured in newtons, which is different from pressure, which is measured in newtons per square meter, which is called a Pascal. The Pascal, if you look on tires, I don't think they're rating tires in Pascals of pressure just yet, but when they talk about the barometric pressure on the radio, they'll talk about Pascals or kilopascals. It's the barometric pressure. Do you need to be able to solve problems with this?
Yeah.
No. In fact, none of this is actually I'm supposed to be teaching you, but people get confused between pressure and friction, so I throw it in. Spend a few minutes talking about it. You don't need to worry about it. I just wanted you to realize that pressure and friction are not the same, and that friction is independent of the area of contact. Is this amount of friction the same as this, is the same as this, provided that the surface is the same. Like if this was a rough surface and this was nice and smooth, that would be different, right? As long as the surface texture is the same, then it doesn't matter. Many people mistakenly believe that the wider tires of drag racing tires produce more friction. Not true. The larger area reduces only the pressure. The force of friction is independent of the contact area. Wide tires produce less pressure, and narrow tires produce more pressure. The wideness of the tires reduces heating and wear. That's why they're so big. It's because they heat up so much. If they were narrower, they would heat up and they would disintegrate right away. Okay? Do you know why race tires don't have treads like this one here?
That's a race tire?
No. This is a regular car tire, but when you watch like NASCAR or something or other, they have no tread. How come?
It needs to be here and they're turning down. Like the treads give more grip.
Like the treads give more grip? Slows them down?
Why tire?
Maybe. There's a lot of different reasons, but number one is simply cost. It costs more to produce these. Why do we need tires with tread out on the street? Because there's things like rain and ice and snow, and what happens is that the tread pushes that stuff to the side and actually allows the rubber to contact the road itself. Do they run NASCAR races when it's a snowstorm and it's ice, the track is icy? No! They'd be sliding all over the place, right? They race in almost perfect conditions, so they don't have to worry about that stuff. They do, yeah, they do that. And I think they probably put special rain tires on too.
Yeah, they have spectral training.
Yeah, they have treaded tires. That's really the only reason, is because they don't race in the rain. Okay. You know what? Blah, blah, blah. Let's get on to that. Nah, I wouldn't even worry about that one. Let's just go right to the video. A dramatic illustration of pressure is shown in figure 412. Pay attention. This will be exciting.
Bears on Facebook teacher minutes.
Really?
Lost his job or something.
Oh.
Yeah.
The author applies appreciable force when he breaks the cement block with the sledgehammer, yet his friend, who's sandwiched between two beds of sharp nails, is unharmed. This is because much of the force is distributed over the more than 200 nails that make contact with his body. The combined surface area of this many nail points results in a tolerable pressure that does not puncture the skin. I'm recording this for legal purposes. Caution. Dangerous. Do not attempt.
On
If
your
you
own.
attempt and you hurt yourself,
It's on your own.
I will bring this up.
We should watch the video on it.
I am telling you, do not attempt
This
this.
teacher who did this, but there like it wasn't nails, and he like missed the.
Yeah, you like
missed
hitting the ball.
Oh, I see that.
Hit his student.
We have to see
in
that.
Right in the private.
Oh, that doesn't sound good. I thought I had a video of this here.
He used an axe though too.
An axe. Okay, well let's answer the questions first.
Search up on YouTube.
I'll find it. Don't worry. In attempting to do the demonstration figure 4, okay, Karen, you gotta start paying attention now.
Sorry.
In attempting to do the demonstration in figure 412, would it be wise to begin with a few nails and work your way up towards more?
I'll start.
Yes or no?
Way to be, Wyatt. Way to be.
Let's see if we can get 100% on this one. Would you start with like 2 or 3 nails, or start with like 400 or 500 nails? Lane, smart enough.
I'm gonna go with no.
I said yes. I said all the time.
No.
Please get it right.
Yes. Who was the one who said yes?
I'm gonna check later. No, do not start with 1 or 2 nails. Start with a lot more and work your way down.
Trick question.
The massiveness of the cement block plays an important role in the demonstration. Which provides more safety? A less massive block, a more massive block, or the massive block? I'm lying, it doesn't matter. I'm talking about, excuse me, I'm talking about this big cement block right here. Concrete, not cement. Which provides more safety? Less massive, more massive, the massive block does not matter.
Of course, that matters. It's like on.
It's like 10,000.
Which one is safer though? Big block, small block?
It's gonna be some kind
I want to see.
No trick, it's physics, man.
Make it's gonna happen. On Wyatt. I gotta make you. Yeah.
More massive block. You want a big block because what you're doing here is you're actually slowing the sledgehammer down, right? And do you want this bed of nails accelerated towards your chest? No, right? And so the more massive block, it has a much less acceleration.
How big can you go if that block goes like 2 times?
Wow, then you might suffocate the guy, I guess, right? Okay. The greater the mass of the block, the smaller is the acceleration of the block in the bed of nails towards the print. Much of the force wielded by the hammer goes into moving this block and breaking it. It's important that the block be massive and it break upon impact. Do I have video of it? I do.
Yeah.
Can you double check that you've got the same question that I have?
Yeah.
We have a box of mass 46 kilograms pulled along a level floor at a constant speed by a rope that makes an angle of 30 degrees with the floor is shown. The force of the rope is 200 newtons plus the horizontal component. What's the normal force and what is the coefficient of sliding friction? And it looks like I've already given, do you guys have this as well? This
No.
FW?
No.
Copy right now.
Well, let's do it. Why do I have it so big though? Let's see if I can make it a whole lot smaller. Okay. Well, as always, 260 degrees, 260 Newton, 30 degrees. Should we start by finding the weight force? Absolutely. We're only going to do one sample, you guys, so keep those phones away and try to concentrate here. Here's where the learning happens. You'd be surprised what a little bit of focus will do for your mark. Should we find the weight force first?
Yeah.
Absolutely. 46 kilos times 9.8. I think it was on the previous page. 450.8. Okay. We'll just pause there for a second. calculator, 'cause I'm gonna need one. Now, if you'll pardon the expression, normally the weight force is equal to normal force. And so this is, well, let's finish part A, I guess. It says, what is the horizontal component of this force? I guess this really isn't part of part A. This is part of B, but regardless, let's go FA is equal to FH is equal to FA cos theta. Right? So that's giving me what? How much of the force is sideways, like that? So that's going to be, what's my applied force? 260 newtons. My angle is 30, so 260 cos 30. $225. 225 newtons is pulling it sideways. What happens to the other, this was 260. What happens to the other, what is that, 35 newtons? 260 minus 225. Or is 260 minus 225, is that anything at all? It's nothing. It doesn't mean anything, right? 225 newtons is being pulled sideways. That's the component that's pulling sideways. But there's also a component that's doing what? Lifting it up. There is a vertical component. When you're moving something heavy, people often lift up a bit. Makes it easier to push, right? So there is an actual vertical component. I'm going to slide this down here. You guys probably have it. You can't do that, obviously. You can try. If there's 450.8 newtons down, how much should there be up? 450.8. But that's the total up. So in this case here, the weight force is equal to the normal force plus the vertical component. The vertical component assists or helps the normal force. Okay, I'm going to redraw that over here for you. And if you want to do this, you can. It's up to you. But, oops, that's not what I want to do.
Fn plus what?
Fn plus Fv. So we have the weight force down, and we have normal force as well as vertical component. The applied force is partially up and goes into lifting up, reducing the normal force. Does that make sense? These two have to, I can't do it. These two have to add up to this one, right? Like so. So, do we need to find the vertical component? We sure do. If the horizontal component is the cosine, because it's adjacent, the FV is over here. That is opposite, which is which of the trig identities? Sine. So FV is going to be FA sine theta. Is that a new formula, a new rule? Is that always going to be like that? Yes. 99.9% of the time. And the reason it's only 99.9 is because if this angle is listed like here, if it's the other angle, then it's going to be opposite, right? But 9.9 times out of 10, the angle is here, so the horizontal is the cos and the vertical is the sine. I can't think of a question that you'll see that it's not like that, but you might encounter that at some point in your career. So I won't say always. So this is going to be simply 260 sine 30. And that's it cos again. $130. Hold on here. I'm telling you that vertically there's 130 newtons, horizontally there's 225, but somehow there's 260 total. Like 130 and 225 don't add up to 260, do they? Have I made a mistake?
No.
I have not. Do not write this down. those of you that have taken any carpentry will know about the 3-4-5 rule. What is the 3-4-5 rule? Helps you figure out if it's 9 degrees, right? Perpendicular. Does 3 and 4 equal 5? No. 3 squared is 9, 4 squared is 16, and 5 squared is 25. 9 plus 16 is 25, right? So should the vertical component and the horizontal component add up to the total? No. No. But if I took 130 squared plus 225 squared, I should get the square root of 260, right? And you'll find that that's true. There might be a little small rounding error, but that's true. Okay, so I've got my vertical component, and I've sufficiently explained that, I think. So now, what is the actual normal force? That's what the question is. What is the normal force? What's the weight force? 450.8. We're solving for normal force. Do you see how writing the formula and organizing things is a good idea? Vertical component, 130. How do I solve for the normal here, Cole?
You gotta get down below.
Yeah. How do I get rid of that plus 130? Divide it?
Plus subtraction.
Subtract, right? It's attached by a plus 130, so we're going to subtract. Minus 130, right? It cancels. So the normal force is 450.8 minus 130. 320.8. Now, why does that matter? It actually reduces the friction force. Okay? Here, let's find out what the coefficient of sliding friction is. What is the coefficient? Well, mu is equal to FF over Fn. That was a formula that you found out on Friday, I think, right? How does it say? How do you pronounce it again? Mu? Yeah.
Yeah.
Gonna go up to the cows and start doing that?
Yeah.
See what they say?
Yeah. I do that all the time.
Do you?
I do that all weekend. All the time. All weekend.
Trying to get the cows to say mu. All right. Now, I know the normal force here. It's this 320.8 that I just found out. But do I know my FF?
Yeah.
I do?
Yeah. Speed.
Aha. Constant speed means what? Not accelerating. Oh, I did not want to do that.
Oh, good.
Constant speed means not accelerating, which means that the sideways horizontal component, Jenny, FH, is balanced by the friction force. They're equal. So that means my friction force is really 225. My friction force is 225. I'm just going to put FH in brackets there. So what is my mu value? Well, it's going to be 225. 225 divided by 320.8. 0.7. Remember, most mu values are less than 1. If you get a mu value that's bigger than 1, either you've made a mistake or it's extremely rough surfaces. Not likely going to... Yeah, like really there, I think there's one question where it's significantly greater than 1, and the answer is the object doesn't move because friction's ridiculous. So maybe even grade 12, I can't remember where it is. Yeah. Something like that, yeah. Velcro on Velcro. Now, does the mu value change when you lift, as you push it across and you lift it a bit, does the mu value change? And the answer is no. The mu value doesn't change. And so, because the mu value stays the same, let me just make a new page here to explain. Let's say in another situation, I've got this block here, and the mu value is 0.5, right? And mu is FF over Fn. If I can reduce the normal force, here's my weight force, here's my normal force. If I can reduce the normal force by introducing some vertical component, if I reduce the Fn, and I want to do this so that I can make this work here. If I can reduce Fn, make it smaller, if the 0.5 must remain the same, because that only depends on how rough the surfaces are, what does that do to the friction force? Makes it what? Greater? If this gets smaller, then to make the whole thing still equal, what happens to friction? It gets smaller as well. Okay? Let me give you an example. If mu is 0.5, and let's say the friction force is 50 over 100, right? Give me a second here. Okay, if the friction force is 50, and if I reduce this down to, say, 80, if I reduce the normal force down to 80 by lifting it, the 0.5 must remain the same, so what has to happen to the force of friction? It goes to 40. It drops. It makes it easier to push. That's why you lift when you push, because it makes it easier. Graham, thank you for waiting.
We might not be here Wednesday because there's that carpentry.
Oh, yeah.
I think it's Wednesday.
Yeah, it is. Mr. Bike was telling me about this morning. Yeah. Some of you might have to write Thursday.
No, stop. I might do it all.
Well, we may have to do that, yeah.
Just do it all.